Chapter 5, Discrete Probability Distributions. So we're going to be covering this chapter for 2 weeks. So I'm going to do half of this presentation now and then half again next week. That's how we can get a little bit more information, and we're going to work on stuff. So as we notice, we have discrete probability distributions. Now we're really interested in discrete values. So what are discrete values? Discrete values, remember, are counting numbers: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Okay, versus continuous values, which have fractional parts to them. 1.361, 2.589, and so on and so on. Why are we interested in discrete versus continuous? Well, discrete happens in real life. We count things. Okay, and so that's why we're really interested in what is happening in the discrete probabilities. So when we have that, we have to have a random variable. Now, it's not necessarily a random variable as in we're just pulling numbers out of the air, but we're asking questions. How many cell phones do you have? Well, I have 2. I've had many, but right now I have 2. And so on. So what is your age? 36. What is your height? 5'10". We're asking people questions. They're giving us an answer. These are going to be random answers, to our group, and thus the random variable that we're getting. Now, when we're done with these, we're going to make a distribution. Okay. A distribution is just a sheet of all of our counts and then the probabilities of getting those counts that we've had. Okay. Now, there's 2 rules for probability distribution. The first is that all the probabilities added up have to equal 1, and the second is that the probability, each individual probability, has to be between 0 and 1. Now, in a lot of cases, we will show that a probability has, we won't count it because we didn't get any, but if we find that a probability has a minuscule chance of occurring, we don't want to put 0 because that falsely assumes that it has no chance of occurring. Because remember, 0 has no chance of occurring and 1 is a definite. But so if we have a minuscule amount, you might see a 0 plus, as I mentioned in the book, and so that's just something to be aware of. Now, when we deal with these probability distributions, we're going to create formulas. Okay. We'll use them for certain things as we go along, and the formulas are the same ones we used before. We have the mean. As you can see here, the mean is the sum of the x's times the probabilities. Okay, frequency distribution, same thing here. Then we have our variance, which is we take our x, we subtract off the mean, we square it, multiply it by the probability, and add all those up. And then to find our standard deviation, we can take the square root of that. Or we can do x squared times the probability of x minus mu squared. This is what our calculators do. It's easier, and thus the reason it's done. And then we take the square root of it. And as you can see from the previous one, if we square both sides, we get our variation again. So now when we're done that, we have kind of chunky information stuff, but one of the things we do get out of that that's very important is the expected value. And the expected value is the same as the mean. Okay. Now we use this in decision theory, and they talk about this on page 212 and 213, where they're asking, well, which is a better bet? A $5 bet on the 7 in a roulette wheel or the $5 pass line in craps? And they calculate how much are you expected to win, or since it's a casino, lose in each case, and you take the higher value. So as you can see in the solution, they've added up the losses of $5, and you're going to lose 37 out of 38 times, and you're going to gain $175, but that's only going to occur 1 out of 38 times. And so they've added up the 2 values, and they find that you lose 26 cents in the roulette wheel overall in the long run. Whereas on craps, you actually lose only 8 cents. So you're better off playing craps than you are roulette if you're going to bet on a single number. And that's the expected value. Now, we also have unusual results that are going to occur, and those are similar to what we've had with regular numbers, where we have the mean plus or minus 2 standard deviations. Anything outside of that 2 standard deviation area is still an unusual value. Okay, and that's really all there is in chapter 5.2. Now we're going to look quickly at 5.3, which is binomial distributions, and then we're going to stop and we'll cover some more stuff next week. So a binomial distribution is again a discrete distribution, except for the fact that there are 2 chances of things happening. You have success and failure. There's a fixed number of trials. The trials are all independent, so if I take something out, it doesn't depend on the last one. There's only 2 possible outcomes, success and failure, and the probability of success is always the same. So when they say a fixed number of trials, I'm going to look at 150 widgets that come across the conveyor belt and see if they weigh the right amount. Okay, they should all, the weights are all, don't depend, no matter when they occur. So the trials are independent. I can either have the right weight or the wrong weight. I can have and my success is going to be the same. It's a 20% chance of success, a 90% chance of success. On every time, the success rate is exactly the same. So what do we do with these? Well, we have our formulas again. These are important. The probability of success is P. The probability of failure is 1 minus P, or Q. The number of trials is going to be our N. The number of successes is what we're looking for. Those are the X's. So the probability of getting exactly X number of successes is P of X. So because sometimes we want to look to see at least that many, sometimes we just want to see less than that many, sometimes we want to see more than that many, but the probability of getting 3 successes out of 5 is that number. And so those are the things you're going to see written down. And I'll show you some of those as we go along. Now, the nice thing about the binomial distribution is that the formulas are really easy. Our mean is n times p. So the number of trials times the probability of success. The variance is the number of trials times the probability of success times the probability of failure. And our standard deviation is n times p times q square rooted. So those are very nice, simple formulas to use. And we can go in and I can see how the things are built by using the factorials on page 221, but we're going to skip that and just assume that they're correct. And then they actually, the nice people in the book publishing give us lists of values in Appendix A. There's also Minitab or the calculator that we can use to calculate these, and we'll show you how to do some of those in class on Saturday. So